Okay, so we're in chapter 3, Matter and Energy. This is of the Timberlake text. What's matter? Matter is anything that occupies space and has mass. So anything that has mass and volume. And if you remember from chapter 2, density is equal to mass over volume. So you can think about anything that has a density is matter. Matter is composed of either atoms. Ultimately, everything is broken down into atoms, so even molecules, proteins, large compounds in our bodies are always broken down into atoms or ions, which are charged atoms. So we have here a picture of an aluminum can, and inside the aluminum can is essentially aluminum atoms. Aluminum cans are also coated with plastic on the inside so that the aluminum atoms don't oxidize in the carbonic acid. Matter can also be composed of molecules. And so atoms that are bonded together, we consider those molecules. And so, for example, isopropyl alcohol, rubbing alcohol, would be composed of alcohol molecules. It is a mixture because there's 70% alcohol, which means 30% is also water. Water is a molecule as well. But eventually, ultimately, you can still break down into atoms. So an atom is the smallest unit that you can break down and still be that element. So an atom is the smallest unit of an element that is still that element. And what I mean by that is that it has the same number of protons as another element of its kind, so it's still identified as that element. So for example, an aluminum atom is the smallest you can get while remaining still aluminum. If you go deeper or smaller than that, you get into protons, neutrons, and electrons, which we'll talk about later. You're no longer an aluminum atom, right? So you can't call yourself aluminum. So how do we see atoms and molecules? Here is an example of some of the latest technology, a scanning tunneling microscope. And we can see that these little blue areas are actually atoms. And so we get that 3D, we can see the atom. Now we can't see inside the atom or individual electrons floating around or anything, but we can see these bumps. We can distinguish those as atoms, which is pretty cool. Here is a molecule. This is DNA. And so you can see the little bumps and ridges kind of looking at the atoms of that molecule, but the whole thing, you can see that double helix structure, which is really cool. So I want to think about 3 different states of matter. We're going to get into these states of matter a little bit more later, but we're going to be talking about phase changes today, and so refreshing your mind on what these states of matter are. We're going to be talking about solids. So a good image for solids is this image that we see here. This image is kind of showing this vibration because solids do vibrate. Then you have a liquid, and liquids are a little bit farther apart. Unless you're water, so don't worry about that, but liquids are a little farther apart in their particles and they're moving more freely. And then we have gases. Gases are very far apart and moving very freely. This image here showing the gas actually is a little bit wrong. I would like to say let's take out all of the gas particles except for one. That's really what this image would look like if it were true to the space of gas particles, because gas particles are really far apart. So in this small image, you wouldn't see these gas particles close together. You'd actually see them, if it were all to scale, you'd see them you'd only see one gas particle, but that's a little misleading. Gas particles are very, very far apart. Alright, so quick recap. In your textbook, you've got a table 3.1, which tells you mainly about a few things I want you to focus on. The shape and the volume is fine. I mean, that's a multiple choice type question, like what to the following has a definite shape, definite volume. You know, solids have definite shape and volume. Liquids take the shape of their container but have a definite volume, and then gases are free in both realms. What I want you to really look at is the interaction and arrangement of particles. So these 3 sections here, interaction, arrangement, and movement of the particles. I want you to pay attention to those because we're really going to start thinking about how particles interact with each other, and that's really the basis of chemistry, so we're going to get a good foundation in that. So classification of matter. So we're going to look at how to classify matter. The problem with classification systems is that if everyone is left to their own classification systems, then you can classify things in all kinds of ways. So just thinking about household things, maybe I classify this cabinet as belonging to cups, and this cabinet is belonging to pots and pans, and that is a classification that I have set aside for myself, like drinking things and cooking things, and that's classification. But then my husband may come in and he may decide that he thinks that the plates and the pots should go together because that's all the things you need for one meal or something, right? So he can classify things differently. And so classification is something that we really have to make sure as a scientific community that we're all on the same page. And so we have this classification system. And we'll come back to this slide. We have this classification system here in this nice little flowchart. And so this flowchart is going to help us break matter down into pieces, pure and mixtures, and then take those pure substances and take those mixtures and break them down even further. So we're going to be using some properties to discern these different arrangements of these different classifications. So let's back up really quick. What kind of properties are we going to be using to classify things? There's two different types of properties that we're going to look at. We're going to look at physical properties and chemical properties, and so you need to know the definition of these two. Physical properties allow you to see that property or to observe or measure that property without changing what the thing is. So for example, some physical properties would be color. I can see something's color, I can write down, observe its color without changing what it is. I can, judge that from afar. Another physical property would be shape, texture, size, etc. Another physical property that's a little more confusing with chemical properties is a melting point and boiling point. And so we're going to talk about phase changes a little later, but a melting or a boiling point is a property that's a physical property. Because if you think about it, can you melt ice, figure out what temperature it melts, and it stay water? Isn't it water before as ice and water after as liquid water? Yes, it's still water. So a melting point is a physical property because it hasn't changed what it is. Okay, so for example, water solid is still water. So water liquid and water solid are still water. So if you're only changing the phase, that is a physical change. If you're saying like, oh, I'm gonna change this from solid to gas or from gas to liquid or whatever, you're only changing the phase, you're not changing the substance. That's a physical property. And so think about, are you actually changing what it is? Because the only way that you can have a physical property is if you do not change what it is. So going over here to chemical properties, some examples of chemical properties would be flammability, would be reactivity. So these things I cannot tell unless I test it, and once you've tested it, it's not what it used to be anymore. And so flammability, let's think about some wood in a fireplace, and it's turning into ash, right? And it's also giving off some carbon dioxide and some water. This is a combustion reaction. Okay, it's reacting with oxygen. So when I burn wood in oxygen, it turns into ash, which is some other carbon compounds, and then it gives off some carbon dioxide and water. Well, that's totally a different compound now. It's not wood anymore. We don't even have the same name for it anymore. So that's an example of a chemical reaction or a chemical change. So if we're dealing with reactions, you're dealing with a chemical change. And if it's not a reaction, if you would say it's more of a process, like melting or boiling, then you would call it a physical change. And so these properties are really going to guide us into deciding what's chemical, what's physical. But right now what we're going to be doing is we're really just going to use physical properties at this point in time. So we're only going to be using the physical properties, right, to tell the state of matter or the state the different compositions. And so moving forward, think only about the physical properties, okay? Now, looking at matter as a whole. And so when I look at matter, I can decide first upon two categories, if it's pure or if it is a mixture. And so I'm looking for pure or mixtures. And I want you to think about the difference between these two as having one ingredient or multiple ingredients. So most of the things that we encounter in our lives are mixtures. Think about something that you have in your household where you look at the ingredients list in the back and it has only one thing. Okay, that thing is pure. That is a pure substance. But if you can think of any more than one thing inside of that compound or inside of that thing that you're using, then it's a mixture. Now, I don't mean that, okay, inside water, there are two things, right? There's hydrogen and there's oxygen. But if you were to look at an ingredient list of water, you would see one thing, water. Unless you've got like electrolyte water or something, right? But if it's pure water, you'll just see pure water. And so that's going to be a pure substance. Now, pure substances can have different atoms in them, or they can have different molecules in them, different atoms in molecules, but the molecules are all the same. So for example, let's look at a pure substance. Once we get in and decided that, hey, there's only one ingredient here, it's all the same thing. So every particle is the same. Every particle is the same. I would say maybe the same name. Alright, and if your particles are atoms, you have some molecular elements. We'll get to those a little later. If your particles are typically atoms, and all atoms are the same, you're an element. So all atoms are the same. So look at this example. Here we have some, I think these are gold, pieces of gold. And every single atom here is exactly the same. So we would call this a pure element because all of the atoms are the same. Okay, so that is our pure element. Now, what if the particle that you're talking about is not an atom? What if the particle that you're talking about is a molecule, or something called a formula unit that we'll talk about a little later? And so if every particle is a sugar particle, then it is a compound. So all molecules are the same. Now, there are different atoms. You can have different atoms, but each piece is the same. And so this sugar molecule is the same as this sugar molecule, is the same as this sugar molecule. And there's only sugar molecules in this. So if you look at the bag of sugar, or the packet of sugar, the ingredients would say sugar, or whatever sugar substitute you're using, they would have one ingredient. So that is a pure substance, but that is not an element. Sugar is not an element. It is a few different atoms bonded together in a very, in a structured way, but each group of them is exactly the same. So it's kind of like either you're copying and pasting individual atoms over and over again, or you're copying and pasting groups of molecules over and over again. But either way, you get the same substance repeated over and over again. That's a pure substance. Alright, so moving forward, we're going to talk about mixtures. And I will pause if you need to get these notes because I'm about to erase it. I'm going to erase all our substance about pure things, and we're going to focus in on our mixtures. Okay, so if you've decided that it's a mixture, you've decided that there's multiple ingredients present, and so now we need to kind of dive in and say, okay, well, is it homogeneous, or heterogeneous? Heterogeneous. Either way you want to say it is fine. So homogeneous. So think about the root homo meaning same. And so if it has the same composition throughout the mixture, What do I mean by that? I mean that this area of my T is the same as this area of my T, hopefully in this area of my T. I could take like a sample from every area of this mixture and it would be the same. And so because I've got water molecules, if we look down here at our molecular view, I've got water molecules and I have some caffeine molecules and I have some sugar molecules, and these are all different molecules, which means that I've already got an ingredients list, right? Water, sugar, caffeine. Those are that's what it tells me it is a mixture, but because everything is dissolved, it's homogeneous. So we also call homogeneous mixtures solutions, and everything is dissolved. Okay, so if you've got some salt water that's dissolved, if you're drinking coffee, coffee is not a molecule, it's a mixture of a bunch of different things, then that is going to be a homogeneous mixture. Versus heterogeneous. So hetero meaning different. So this has a difference in composition. Meaning you can tell there are different parts to it. So for example, we look at this oil and water. We have a defining line. Up here is oil and down here is water. There's an obvious difference. First of all, in the whole sample, I've got two separate types of molecules, so it's a mixture. But because they're completely separate, if you were to take a sample up here and a sample down here, they'd be different samples, right? So that is heterogeneous. Another example of heterogeneous would be like pepperoni pizza. Like if you don't have pepperonis, take it off. You can tell that there's different pieces to the mixture, and that means it is heterogeneous. And so think about homogeneous meaning the same throughout, heterogeneous is different. So think about taking samples from your mixture. If all the samples are the same, homo, all the samples are different, hetero. Okay. So here's another couple of examples. A pure substance, so here's some helium atoms floating around. We can see that all the atoms are the same, and so this would be a pure substance and also an element. Here's another pure substance. A water molecule is a pure substance that is a compound. Okay, it's the same molecule repeated over and over. So remember, like we're thinking, let's just copy and paste it over and over and over and over again, and that is a pure substance. Then we have mixtures. So if you look at the air is actually a mixture. We do not breathe pure oxygen. If we breathed in pure oxygen, we would be first of all, high all the time. Second of all, every time you would light a match or light your stove, the whole world would explode because oxygen is the fuel for any combustion reaction like that. And so we got a lot of nitrogen in the air, we got some oxygen, and every time you breathe out some CO2. There's some carbon monoxide hanging out in there, hopefully not in too high levels. And if you live in like Los Angeles like we do, then you probably got some other kind of soot and things hanging out in the air, so making it a little bit smoggy and cloudy. There's actually a lot of water in the air as well, water vapor. So an air is definitely a mixture. Now clean air is a homogeneous mixture because hopefully you could take a sample from one part of the air and another part of the air and it would be the same throughout if it's clean air. Now I know in the atmosphere there are layers, right? But don't think about that as I'm talking about just like you have some air in a bottle or in a jar and you're going to sample it, it's going to be the same throughout. And then you have your seawater, and again, just assuming that it's very, 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 very clean, that your seawater is just salt and water. Now, if you've ever been to the ocean, you know that it's also seaweed, and there's little pieces of dead animals and things, dead sea creatures and coral and all that kinds of crazy stuff in the water. But let's just imagine it's like salt water, right? And so you can see here, if you were to take a sample over here and you were to take a sample over here, you would have the same throughout, right? So those are going to be your homogeneous mixtures. Now I want you to think about what a heterogeneous mixture would look like. Let's say I took a sample right here and I scooped up some sand with some water. The sand does not dissolve in the water, and so that would be a heterogeneous mixture because I'd have water, salt water on the top and sand on the bottom. So I'm going to kind of skip these. We're going to do some examples in class, but if you would like to pause and go for it, the answers are going to be in the slides and the speaker's notes. So we've talked about this before, but physical changes are anytime you change states of matter, that's going to be a physical change, or anytime you change the appearance of something but not its composition. So coloring something by placing color on top of it is a physical change. But if you were to color your hair, dye your hair, that's a chemical change because you're actually stripping the color or placing color on. So don't think so much about anytime you see a color change. Like dyeing is a little bit different. Chemical reactions occur there, but just coloring on top of something or painting on top of something would be a physical change. But essentially ask yourself this question. It's the same substance before and after. Okay, so same substance before and after. Versus a chemical change, totally different substance after the process. If you have iron atoms turning into rust, that's iron 3 oxide. That's not rust anymore. I mean, that's not iron anymore. It's iron, and the oxygen comes in and makes it a totally different thing. We're going to see a change in its physical properties as well. So we're going to see this shiny gray metal turn into this, you know, other type of texture. What is the rust texture? Like a grainy texture, and it's going to be maybe a little red or a little copper colored, and so you've got something totally different that has happened. That's a chemical change. And so how I write chemical reactions, I write reactions with a line in the middle. So this here is my yield sign. Okay, so I want you to know that this is a yield sign. We'll talk about this a little more when we talk about balancing reactions. But we have words like reactants and products. So reactants, I want you to think about as your ingredients for the chemical change. And products are the products of the chemical change. So I put some stuff in, I get some stuff out. That would be how we tell a chemical reaction. Now, can you also do this by saying like, oh, solid water goes to liquid water? You can denote a physical process using this method, that's fine, but typically we reserve this for chemical changes. So here's another couple of examples. If you were to let liquid butane turn into a gas by just opening the lighter here, we'd have a physical change. Butane in the beginning, butane in the end. But if you were to actually strike the flint, you've had butane in the beginning, and then you have carbon dioxide and water molecules in the end. Also, you're giving off lots of heat, which is another indicator of a chemical change. So here's some things that are not chemical reactions. So putting food coloring in water is not a chemical reaction. That is a mixture of food coloring particles and water particles, and making a mixture is not a chemical reaction. Boiling water is not a chemical reaction. It's still water before and after. And this image over on the right is dry ice sublimating. And so dry ice sublimating is a phase change as well, not a chemical reaction, even though it looks cool. And in my PDF, the video doesn't play, but if you want to see this video, it's in the slides, and this dog is blowing bubbles in his water bowl. That's not a chemical reaction. As cute as it is, he's just blowing the same gas out of his body into bubbles. And so just because you see bubbles somewhere does not necessarily mean that a chemical reaction is occurring. And so if you want to get some practice here, go into the slides and check your work. So we can separate mixtures. We'll talk about this a little more in the lab section, but you can separate mixtures through a process called distillation, and a distillation is a separation based on boiling point. So separation based on boiling. So if you start heating something up and you've got a mixture, the thing that has the lowest boiling point is going to turn into gas first, and so that gas is going to travel up here. It's hot, it gets condensed with this cold water running through this condenser, right? So cold water running through a condenser, and then it's going to condense into a liquid, and it's going to drop into this container here. And so you get the thing that's going to boil first coming out first, change your receiving flask to get your next substance out, and that's how we separate based on distillation. So when something says it's been distilled, that's what that means. You can also separate mixtures based on filtration, and filtration separates based on, so separation based on size. You've done this if you've ever used a colander for anything in cooking. And so you've got your the solid particles are too big, they can't fall through the filter paper, and you have your liquid component of your mixture being separated down here, so filtration is a separation. So one big thing we're going to look at is the law of conservation of mass. You can also know it's the law of conservation of matter as well. It's the same idea. There's no new matter. Matter is neither created nor destroyed. In a nuclear reaction, however, we can have significant changes in mass because the mass is being converted to energy, but we're not going to be looking into nuclear reactions. Chemical reactions, it's so small that we can ignore that, okay? So here's an example. If you put 266 grams of butane and oxygen into a combustion reaction, you get 266 grams of total product out. So law of conservation of mass says what you put in is what you got to get out. Alright, so switching gears a little bit, we're going to look at energy now. The last half of this chapter is all about energy. And so energy is the capacity to do work. All reasons that things happen. So anytime a chemical or physical thing happens, it is because there is some sort of energy being put in or energy being given out, and it all has to do with how much energy is available to do the work. That's called free energy. So if the substance has a lot of free energy, it can spend free energy. If it doesn't have a lot of free energy, then the process is probably not going to occur. So it kind of drives everything that matter does. And so the law of conservation of energy states that energy cannot be created nor destroyed, just like the law of conservation of matter. Energy is only transferred. So here's some energy numbers that you can kind of think about. I want you to know a joule is the unit for energy that we're going to be using. You can also use a calorie as a unit for energy. We're going to be using mostly joules and calories here. So again, here's some units of energy. I will be giving you these units, so don't worry about memorizing them. You may get to a class in physio where they want you to memorize. I would say if they do want you to memorize anything, it's probably going to be this conversion right here. But as far as this class is concerned, again, I'm going to be giving you these conversions. Now be careful. Look at this. Calorie equals 1,000 calories. So when we see calories on your food, right? Let's say like, oh, I'm eating something and it's 160 calories. That's a big C calorie. So that's really 160 kilocalories, which is really, move our decimal 1, 2, 3 places. 1, 2, 3. That's really 160,000 little calories. So what do you think is better for the consumer? To tell them that something is 160,000 or to tell them that something is 160? So they've changed the unit to better represent easier math for people who are counting calories, right? Now, in the US, you don't see kilocalorie. You see big C calorie because we don't use the metric system. So it's catered to us. If you go other places, you may see the kilocalorie as an option. You may also see actually kilojoules or joules for an option as well as far as energy of food that you eat. So look, calories are not bad. It's energy. So when you're looking at the calorie intake of food, it is just literally how much energy that food is going to give your body when you burn it. That is all that means. So don't have this bad stigma about calories, because guess what? You need to intake energy. You need to intake fuel. And so we have a few different types of energy we're going to be talking about in this course. I want to focus mainly on these two, kinetic and potential energy. So kinetic energy is the energy of movement. And potential energy is the energy that's stored. So that is going to equal your total energy. So if you're moving and you have stored energy, then you have a total energy, right? And so that total energy is something called enthalpy, which we'll talk about in a little while. So how do I know what kind of food has what kind of calories? So we use something called a bomb calorimeter you see here. And so you're going to burn some food in this combustion chamber. We run some oxygen through these tubes to make sure that there's enough fuel for the fire to keep burning. And then we have an insulated container and we stir some water around and measure the temperature of the water. Now, we do not measure the temperature of the food burning because a thermometer cannot probably handle that. So we measure the temperature change of the water to help us figure out how many calories it is. And I'm going to show you some math that we'll use to help us with this. But what I want to note here is the direction of the energy flow. So where is the energy being produced? It's being produced by the food. And where is it going? It's going into the water. So the heat, the energy flow is from hot to cold. So the water's temperature should rise or fall, right? We should see the water's temperature rise. And so a thermometer is always measuring the environment. So if you see something, temperature go up, that's because the thing that's happening is giving off energy. If you see the temperature go down, that means the thing that's happening is using energy. And so we'll think about that when we talk about enthalpy in a second. And so one more quick thing, looking at your nutritional facts, I've gone through this before, but the difference between calories and kilocalories, so be really careful whether or not you're capitalizing your C or writing a lowercase c, because this matters here. And so you may want to, in your nutrition program or something, you may want to be guiding a patient or a client toward a certain food type. So you've got the three main food types: carbs, fats, and proteins. Now, for fast energy, fats are great, which is why Cliff Bars have a lot of fat in them, right? Because you are supposedly doing something, active, and you need some quick energy. So yeah, you're gonna have a lot of fats, and you're probably gonna have some proteins and stuff too. But for fast, quick energy, accessible energy, fat's the best because it gives you the most bang for your buck. It gives you 9 kilocalories per gram, versus carbs and proteins only give you 4 kilocalories per gram, but they're useful in other ways too. So we need all three to maintain a balanced diet. Look at this right here. I just want you to take a quick peek. That should look very familiar to you, and you can guess how I'm going to want to use it. So what I want you to think about every time you see information like this is that this is a conversion. If you can use a conversion, we now have a conversion between kilocalories and grams, or kilojoules and grams. And so if I'm using a carbohydrate, I have 4 kilocalories equal to 1 gram of that carbohydrate. Or I have 38 kilojoules equal to 1 gram of fat. And then I can tell you, like, hey, I'm going to eat 50 grams of fat. How many kilojoules or how many kilocalories is that? And remember, kilocalories are the same as big C calories. And so you can weigh out how many carbs or how much fat you're eating and figure out how many calories that's going to be. So looking at some foods, breakdown, and the energy that you get from it based on how many grams of each thing. So these numbers are gotten from using these conversion factors. So this would be 4 kilocalories equals 1 gram, and they took the 15 grams and multiplied it by 4 kilocalories. Oops, kilocalories to get that 60 kilocalories there. Alright, so we're going to focus mainly right now on potential energy. So potential energy is that stored energy. So for example, this weight has a high potential energy, and I want you to think about high potential energy as being unstable, and low potential energy as being very stable. So the weight up here at the top is not very stable. It's got some kinetic energy here, but then it's hitting the ground here and it's got a lower potential energy, so this is more stable. When you're looking at reactants and products, we have two different ways we can look at that. Either an exothermic reaction or an endothermic reaction. For an exothermic reaction, your reactants are unstable and your products are more stable. And when you go from reactants to products, you release energy. And so if your substance, so let's say I have a flask and I'm trying to measure the temperature, so I'm going to draw like a hand. So I'm touching the flask. Alright, that's a hand, leave me alone. So I'm touching the flask, and I have some chemical reaction going on in here. If it is giving off energy, what am I going to feel? Hot or cold? I'm going to feel hot. So an exothermic reaction, heat is exiting. So I would write the heat as a product. The heat is a product. It's a result. It is coming out with the other products. And if I were touching something exothermic, I would feel hot. So heat exiting is a product for exothermic, and we feel it as hot. Because remember, we're not looking at, oh, it's giving off energy, like I am giving off energy. No, we're looking at it from the perspective of the chemical reaction. Versus an endothermic reaction. If you were to run an, oops, let's just change that color, it's going to bother me. If you're looking at an endothermic reaction, okay, I got my reaction going on here, and I'm going to touch it. Oh my gosh, okay, how many fingers do we have? I'm going to touch this reaction. What am I going to feel? Which way is the energy being pulled? The energy is going into the reaction. So what am I going to feel? I'm going to feel cold. And so we have the energy, the heat, entering as a reactant. It's an ingredient. I have to put energy in to get it to go, because look at the stability. My reactants are already really stable. Why would reactants turn to unstable products? Well, you have to add energy to do that. And so where is the substance getting its energy from? Well, if you put your hand on that flask, it's going to pull the energy from you. And so you're going to feel cold. And so we've got some different phase changes to look at. And you've probably seen most of these before, but just make sure that you kind of get the terms down again. So we have our solid, we have gas, and we have liquid. And just give a quick pause and review these terms: vaporization, condensation, melting, freezing, deposition, and sublimation. Between these different phase changes, you'll need to know those. And then they have a nice little thing of heat absorbed, which is endothermic, and heat release, which is exothermic. Okay, in that direction. In the slides, you can play this video to show the difference of the movement of particles in hot and cold, which leads us into temperature. Alright. Definitions. Alright. We use the word heat as a noun, but it's not a noun. It's a verb. It's a transfer of thermal energy. So heat is a transfer of thermal energy. So you do not have heat. When you touch something cold, there you have heat, because you have a transfer of that energy. So thermal energy is really just the kinetic energy of the atoms and the molecules. And at temperature is a measure of that kinetic energy. So what is a thermometer measuring? It's measuring the movement of particles. And so your thermal energy is your kinetic energy. It's the same as the movement of your particles. When you measure your temperature, you're measuring the movement of the particles. But heat is when you have a transfer of thermal energy. So two things coming into contact with each other can transfer that energy. And energy always moves from hot to cold, from high kinetic energy to low kinetic energy. Now when we're talking about temperature, we're going to be talking about all these different temperature scales. We got Fahrenheit, we got Celsius, we got Kelvin. And so this kind of helps you figure it out. So if you're more comfortable with Celsius or Fahrenheit, you can think about it in terms of Kelvin. Take a note and look at Kelvin over here for me. What's special about Kelvin down here? This is absolute zero, if you've ever heard that phrase before. Absolute zero is when we literally have no more movement. So Kelvin is really, I want you to think about it as a direct measurement of the kinetic energy. It is the only temperature that actually directly proportional, is this little fishy looking thing. It's the only temperature scale that actually measures the kinetic energy. So Kelvin kinetic. So 0 Kelvin means 0 kinetic energy anymore. Things cannot exist at absolute 0. And so Kelvin is our absolute scale. We're going to be using that when we talk about gases. But for right now, we're mostly probably going to be using Celsius, and then so you may need to do some conversions. Here are some conversions where you will get these conversions on your equation sheet. Just make sure you know how to use them. Make sure you take a look at your sig fig rules here. This is infinite sig figs because this is a definition, and these two are also infinite sig figs. So don't worry about sig figs for these because they're constants and definitions. Only worry about the sig figs of your inputting numbers. So if you want some practice, we're going to do this in class, but go ahead and get some practice. Check your work in the speaker's notes of the slides for these two. So heat capacity. What is heat capacity? There's two different types of heat capacity, regular heat capacity and specific heat capacity. We're probably going to be using specific heat capacity more because it actually has a mass of the substance in it. But essentially what we're doing with heat capacity, it is how much heat, so the quantity of heat required to change the temperature by 1 degree. And then specific heat capacity uses a mass as well, which is relevant because the amount of heat you need to change the temperature is going to be affected by how much you have. So here are some specific heats. Look at these units. Calories per gram degree C and joules per gram degree C. This unit will tell me what this specific heat means. Calories. You need to know that calories and joules are heat units. And so how can I write this again? I can write this as calorie per gram per degree C. So how much heat per gram per degree C? And that is your definition of heat capacity. So specific heat capacity tells me if something has a low specific heat capacity. So I like to look at aluminum first. Aluminum has a lower specific heat capacity, not than a lot of other metals, but lower in general. We're going to compare aluminum and water. So if you've ever put something in an aluminum pot to boil, you know exactly what I'm about to talk about. Put my aluminum pot down, I put my water in. I turn my stove on for 30 seconds. Which would you rather touch, the aluminum or the water? Right, you'd rather touch the water. After 30 seconds, the water is not going to be hot yet, but the aluminum is already going to be hot. And so we use these metals with these low specific heats because they conduct heat very well. They conduct this thermal energy change. But water, look at how high water specific heat is compared to everything else. It is so high. So water can take a lot of energy and it won't move its temperature. And you know this. Water takes forever to get up to 100 degrees Celsius to boil. It takes a long time. If you have ever swum in a pool at the beginning of spring, the water is still freezing cold. It hasn't got enough energy from the sun yet to warm up. But if you've ever swum in a pool in like the late or mid-fall, it's probably still warm because it got all that energy from the sun over the summer and now it's holding on to that energy. This is why living on the coast is a more moderate temperature because there's so much water in the air. Your temperatures are not going to be solely determined by the sun being up or not. If you live in the desert, as soon as the sun goes down, it is cold out there, man. But if you live on the coast, you have a more moderate temperature because there's so much water in the air holding on to that energy for you. And then we also use water in coolers because all the energy being given off by the food or the environment is being absorbed by the water, and the water is not going to change its state of matter very easily. And so because of the high specific heat of water, it resists change in temperature. By adding energy to it, you can't really change its temperature very much, which is great. So there's going to be some math. This is just going to be algebra. We're going to do more practice with this in class. Again, you can practice this if you want to now, or you can wait to practice it in class. So for math, you're going to be using this formula. Now I'm going to change this formula a little bit from your textbook. I want you to use the variable Q for heat. We're going to use M for mass. And then I changed these two because it makes a nice little saying for this equation. Specific heat, we're going to use C. and then we're going to use the change in temperature. So delta means change. So let's look at this equation really quick. So I want you to use this equation here. This is the one you're going to get on your periodic table. For Q, Q is your heat, M is your mass, C is your specific heat capacity. And so we can think about, look at all the C's. Look at all the C's hanging out in this word, specific heat capacity. There's so many C's, and so that's your C. And then your delta T. What is delta T? Delta T is your change in temperature. So it's your final temperature minus initial. Any change is always final minus initial. So do some math, find your change in temperature, multiply it by your specific heat capacity, multiply it by your mass, you get your heat. Identify what variable you're trying to solve for, rearrange it, and then plug your numbers in. And so we'll be going over examples of how to do this in class, but go ahead and give it a try, see what you get. I give you the specific heat capacity here, you have your temperature changes, and you have your mass, and they want to know how much heat, so they want to know about Q. You can check your answer in the speaker's notes of the slides. Alright, moving along, heating curves. The heating curves are super cool. We'll probably actually talk about this one a little bit more in class to make sure you have the right idea. So let's check out this heating curve and like kind of build a story as we go. So let me make this as big as possible. Okay. So look at the first part of the heating curve. Let's go all the way down here to the bottom. We're going to work our way up. So starting down here, I'm at a solid. I start to add some heat. Okay, so I start to put this solid on the stove and heat it up. And as I add energy, my temperature goes up, right? And that makes sense. So I add energy, temperature goes up. Add energy, and my particles get more kinetic energy because I'm adding energy, and that makes sense to me. That also makes sense to me from this line. So add energy, temperature goes up. Add energy, temperature goes up. So on all of my slanted lines, if I add energy, the temperature goes up. By looking at the change in temperature. Now that makes sense to me. Increase the temperature because I'm increasing the heat. Cool. But look at these lines. Look at this line. And look at this line. These lines are flat. So what does that mean? That means that I'm adding energy. I'm adding heat. But my temperature is not changing. Okay, so I'll say that one more time. You're adding thermal energy, you're heating it, but your temperature does not change. So, what are we doing with that energy? Because the energy is not going to kinetic energy. So here, on these sloped lines, energy, so thermal energy, is being converted to kinetic energy to change the temperature, right? But here, to change phase. Just check out the images. So in a solid, my particles are very close together. And we can't use Q equals MCAT for these flat lines because there's no change in temperature. If you try to use Q equals MCAT for these lines, you get a Q of 0, but I actually see there is a Q here, and it's pretty big. And so on these lines, we're going to use a different thing. So we're going to use Q equals N delta H. We're going to talk about what that means in just a second. Cooling curves are opposite of heating curve. Same idea, just remove the heat. So we're going to be looking at the heat of fusion and heat of vaporization. And so we're going to for heat. So change in the energy, so change in the heat of fusion. Using the heat of fusion. And I'll give you that number, and it's just a conversion. Okay, so you're just going to be using it as a conversion. Now the other change you're going to look at, so this is heat of fusion. The other change we're going to look at is vaporization. So this is the heat, the enthalpy of vaporization.